Problem 16.73 involves this sphere that we're going to place onto this conveyor belt here. Conveyor belt is moving at a velocity v1 in the I direction. We're told that the coefficient of friction between the sphere and the belt is mu sub k. We're not given the mass or the radius of this sphere. We're asked to find out how long does it take before the sphere starts rolling without sliding. So find that time there. And then the B part is to find what the velocity and the angular velocity is at that T1. All right, we're going to look at a couple of things here. Let's consider the ball right here. Look at the forces acting on it, the mg and normal or frictional. We know that there's no motion in the vertical direction, so the normal force is going to be equal to mg, and there's no other forces in the vertical besides those two. Frictional force is the only thing that's horizontal. We know it's equal to mu times the normal. Normal is going to be mg, so we get mu sub k mg. Now let's look in the A part. We're going to sum the moments about g here, and the only force producing a moment is F, and it's at a moment arm of r, even though we don't know what r is. It's F times r then, and that's got to be equal to I bar times alpha. So F is mu sub k mg, and then times r, and then I bar is 2/5 mr squared for a sphere, and times alpha. So when you solve for alpha, you get a 5/2 mu kg over r. We know that this is a constant angular acceleration right here, so the omega is going to be written as the initial angular velocity, which is 0, plus alpha times the T1 that we're talking about trying to find. Now let's look at the forces that are acting in the x direction. We have F is the only one that's got to be equal to m times A, and that's going to be mu sub k then times mg. And so A is going to be mu sub k times g, and so therefore A is also a constant. And so we can write down the velocity expression, v is equal to v naught plus A times the T1. V naught is going to be 0 because that's where we started out with. We also know that the velocity of the center is equal to the velocity of the point in contact, and once slipping is stopped, the velocity of the point in contact is going to be the same as the velocity of the conveyor belt. So that means that the velocity of the center is going to be equal to the velocity of the conveyor belt minus omega r. And the reason why it's minus omega r is because I'm treating these like they're positive terms. And if you talk about omega being a positive term out of the plane of the board, which it's going to be for this particular motion, you're going to have omega k crossed into rj, and that's going to give you a negative I unit vector. So that's why it's v equal to v1 minus omega r. Now, v1 minus omega r then is the same thing as this right here is equal to v, and v is equal to mu sub k g t1. So we have v1 minus omega r equal to mu sub k g t1. We have v1 minus then omega as alpha t1. So we have alpha t1 times the r and the mu kg t1 here. And so when you get all these together, plug in what alpha is up here, 5/2 mu sub k gr, and right there, and solve for t1 out of this, you'll get t1 equal to 2/7 v1 over mu sub kg. So what you have then is that, and if you want to get the velocity right here, the velocity is going to be equal to A times T1, and A is mu kg, so if I multiply mu kg times this, I'm going to end up with 2/7 v1, so there it is. And then omega is going to be alpha times T1, and alpha is this term right here. Mu kg's are going to cancel out there, and I'm going to end up with the 2 and the 2 would cancel, and the 5 and the 7 will stay, so I'll end up with a 5/7 v1 over r in the k direction.